Yeah, welcome. So in the last lecture, we have discussed about alpha beta pruning. We'll continue with our discussion. So we have discussed that with alpha beta pruning, the time complexity that we can achieve is order of it's order of b to the sorry it's order of b to the power m by 2, right? So this is what we have discussed, but there is a catch here. This is the best case time complexity. This is the best case time complexity that can be achieved with alpha beta pruning. This is not the worst case time complexity. Actually, the worst case time complexity is still it is same as order of b to the power m, which is same as that of the minimax search or a depth first search. So so how can we achieve this best case time complexity? So to achieve the best case time complexity with alpha beta pruning, it should be of perfect ordering. The tree should be of perfect ordering. What is meant by perfect ordering? Say for example, this is this in this case, this is not a perfect order. So this is not a perfect order. So it is considered as a bad or worst case scenario. Why we are calling it as a worst case scenario? So this is a high level representation of the uh, alpha beta pruning tree, pruning a particular algorithm. Say this is the root node. Say from the root node you are performing a max operation and you are getting into 2. So actually you are not getting into 2. From the root node you are choosing something, uh, whatever the max path, then it is minimum return, right? So here the min will choose 2, so on and so forth it goes, so on and so forth, min max, it goes on like that. We don't know how much depth it goes. Finally finally the value backed up at this level is 2. This is what the thing. Okay, so now this node has to explore the next child. When the root explores the next child, again here the same procedure it happens. Alternatively, the max player and the min player plays, and finally the backed up value at this position is 3. Okay, similarly when this node is explored, the two players, the max and min, they play alternatively, and the backed up value at this position is 4. Now now the game should take which move? This is a Now after exploring all these things, the game will make this move, because this is the one which maximizes the profit, or the maximizes the value of the max player. Okay, similarly at every round the min, similarly if you see the next here, this is min's move. So min is first exploring 6, he backs up 6, but min's objective is to minimize. So this is min path. So min also, uh, the objective of the min is to it his objective is to minimize. So he first encounters 6. So he first, actually he is backing up 6, but then the other path he got 4, so he replaced with 4. But in the other path he got 2, so he replaced with 2. So min also, he has to explore all the thing. First he has to explore 6, 4 and 2, then only he can assure that 2 is minimum. So the point is, this is here, in case of worst case scenario, there will not be any pruning at all. There won't be any pruning happening in the alpha beta tree. If there is no pruning, then it is same as that of the minimax, or it is same of the depth first search. So its time complexity will be order of b to the power m. But in the worst case, but in the best case scenario, maximum pruning will happen. Let us assume this is the scenario. In this scenario, what happens? First, the algorithm proceeds in the depth first search fashion, and the value backed up at this position is 4. Okay, now the algorithm will explore this it will, but here the beauty is the algorithm will explore only one path of this node. Whatever the node here, if you take this first level here, all nodes were explored. That is the first child. If you take the first child of the root node, it's every child will be explored maximum. Okay. But if you take the second child's first, only the first child's entire branch will be explored. Why? Because after exploring this, we got here the backed up value is 3. So this backed up value, this is for min. So min means it is beta value. This is max. So this value 4 is for alpha. So here alpha is greater than, so at this point here alpha value is 4 and beta value is 3. So alpha is greater than beta. So the rest of the things will be pruned out. But that doesn't happen here. Okay, but such a scenario here, it is not coming, because initially it is what 2. So at first we don't get here 2. So at first we don't get here 4. It will be 2. Okay, so when the first time it will be 7 is backed up, you can see. So 2 comma 7, it is not greater, then it is 5, then it is 3. So everything is explored. But in the second scenario, that is not the case. So we are able to prune. Similarly, in the next level also, similarly, in the next level, if you see, I mean, for this child also, we explore this child and we explore the leftmost branch of this child. But other things you need not explore, because after exploring this branch, the value backed up will be 2. Again, at this point here, alpha will be 4, beta will be 2. So alpha is greater than beta, so the rest of the things can be proved. So this is the best case scenario. So the point is, if the tree is ordered, if the tree is in this ordering, then alpha beta pruning will give the best performance. So 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 if the tree is ordered in such a way, then its time complexity will be order of b to the power m by 2. Whereas in this case, still its time complexity will be order of b to the power m. Okay. Now the question is, how will we order that? How could we reorder the tree? Is there any way to reorder the tree? Yes, there is an interesting way to reorder the tree. We will be discussing that in the course of this lecture. Okay. So this is the crux of it. So alpha beta pruning provides this time complexity under the perfect ordering, right? Okay. So these are the properties of alpha beta pruning. So even though we prune, it is not going to affect the final result. That means we'll get the same result like what we get in the minimax search. So good ordering of the tree will improve the efficiency. With perfect ordering, we achieve the time complexity of order of b to the power m by 2. It doubles the depth of search. What does it mean? It doubles the depth of search means what? It doubles means, say, uh, assume that, hmm, how can see, it doubles the depth of the search in the sense, say, okay, say assume that the solution is available at depth 8. Solution is available at depth 8. Okay, initially assume that the tree is not ordered perfectly. Initially assume that the tree is not ordered. Okay, and say that now our algorithm is able to go only up to depth 4. After reaching depth 4, either we are running out of time or we are running out of space. Something is happening. Assume we are running out of space. After reaching depth 4, we are running out of space. Let us assume a big value for b. Say b is 35. As b is 35, there are many nodes explored even till the level of 4. So we are unable to proceed beyond 4. But the solution is available at depth 8. And the tree is in a not ordered fashion. Okay. Say that now we are ordering the tree. Now the tree is ordered. If the tree is ordered, it will double the depth of the search. It means previously we are able to continue the search only up to the depth of 4. Now we can continue the search up to depth 8, which means we can reach the goal state, right? So this is one of the advantage of reducing the time complexity. So when you reduce the time complexity, which means you can go more deeper. So that's the whole point. You can go more deeper. So because previously you cannot go that much deep because you are running out of time. Now you can go more deep. So when you go more, so how much you can go more deep? In the sense, it is a double that of the case before ordering, right? Okay. So alpha beta pruning also does something called as meta reasoning. Meta reasoning means reasoning about reasoning. Okay, so why we are calling meta reasoning means it is reasoning about reasoning. Why we are saying it is reasoning about reasoning? Alpha beta pruning itself is a form of reasoning. Alpha beta pruning itself is a reasoning. So this itself is a reasoning. What kind of reasoning here we do? Here for every node we assign an alpha value and a beta value, and whenever alpha is greater than or equal to beta we prune. So that itself is a reasoning. But once again, in alpha beta pruning we further perform another reasoning that is called as ordering. So this ordering, why we are doing? To improve the efficiency of alpha beta pruning. Okay. So alpha beta pruning itself is a reasoning algorithm. So if you call this as reasoning algorithm 1, then we are using another reasoning algorithm called ordering. And what purpose we are using this reasoning algorithm ordering? We are using this reasoning algorithm ordering to improve the performance of alpha beta pruning. So this can be considered as meta reasoning. So what we are doing with ordering can be treated as meta reasoning. So we do order to improve the efficiency of the alpha beta pruning, and hence it is called as meta reasoning. Okay. Fine. So how can we perform node ordering? So one of the easiest method to perform node ordering is to use iterative deepening search, right? So use iterative deepening search. We have learned about iterative deepening search. So using iterative deepening search, then now the depth we gradually increase. Initially we set the depth as 1, initially we set the depth as 0, then 1, 2, so on and so forth. So when the depth is 1, you will find the node which is more promising. Now explore only that path. Okay, that is when you then when you set the depth as 2. Okay, before that you have set the depth as 1. When you have set the depth as 1, we know which path is more promising. So that is max turn. So what is the max value? That node, that path alone you take. Ignore the other paths. Okay. So not ignoring. So we know which path has taken. Sorry, the point is, say this is the case. Say how the iterative deepening depth first search works. It checks whether the initial state itself is the goal state or not. Okay, so it checks initial state itself is the goal state or not. No, it's not the goal state. So then increase the depth. Depth becomes 1. Now explore all its child. This child will be explored. Here exploring means what? It is alpha beta pruning. So this entire should be explored and some value will be backed up here. Say the value backed up here is 2. Okay. Now explore its another child also. Some value will be backed up here as a result. Say the value backed up is 3. Now explore this one. Here, say the value backed up is 4. Okay. Now we know this is a max node. So we know that this is the best one. So it should be ordered in the reverse way. First 4 should come. Then 2 should come. Then 3 should come. Then 2 should come. So like that it will order. By ordering this, what will happen? We can prune more. So when you apply like this, we can prune more. Okay. So actually here we are limiting the depth, so it won't go up to, it won't, there is nothing like backing up, right? I said backup, so there is no backing up business here. Huh. Yeah, I'm sorry, there is no backing up. See, initially there is a node, we set depth as 0, we check whether this is the goal. No, this is not the goal. Now explore only all its child to explore and identify its value. Say this value is 2, say this is a max node, so we are talking about all alpha. Say this is 2, this is 3, this is 4. Now we know that this has the highest alpha value, so this should come first. So this should come first, and then 3 will remain, and then 2. Okay, so now we know that this is the most promising path. So these two paths can be straight away can be ignored. Now similarly, this is min term. Now when you explore, now still the solution is not reached, so we increase the depth by 2. Now increase the depth by 2. Okay, so when you increase the depth by 2, now we know that this is the most promising path. Here you explore this node's child. So this is a min node, say this is 7, this is 6, this is 3. So this is a min node, so again it should be reordered. This will become 3, this will become 6, and this will be 7. So this will follow this path, so on and so forth, you continue. Okay, so that is what the concept of. So so here we can take the support of iterative deepening search to do this. But here you should get one question: how we evaluate these values? Because in case of alpha beta pruning, what we have discussed, only the leaf node will have the values, the what you call the utility values, what is available only in the leaf node. There are no such values available in other nodes. So how do we calculate these values? So actually that is a tricky thing. So that is the challenge in doing, in performing this reordering. Okay, so but reordering still, it it provides great advantage. So we have to reorder, then only we can reduce the time complexity. Okay, fine. So let us assume that we have reordered, somehow we reordered, and we are able to achieve the time complexity of order of b to the power m by 2. So if we achieve the order of b to the power m by 2, then then when you apply to the chess game, how many states it will create? It will create this many states. So this number of states is lesser than the number of states in the universe. So it means that with with this much power, now we can solve this chess game. Okay, but still this is a very huge number, this is not practical. But still this number is very high, this is not practical, still we should reduce it. So how do we reduce this further? Because it is not at all practical. Okay, so to reduce this further, so here the point is, if it is ordered properly, if it is ordered properly, we can achieve at this level. Okay, but still we should reduce this value further. So how can we reduce? So we can reduce by using a technique called cutting off search. Okay, by using a technique called cutting off search. This cutting off search uh, is also called as imperfect real-time decisions. So I'll come on to that. So we can do something called as cutting off search. So what is meant by cutting off search? So if you take normal alpha beta pruning, it goes all the way up to the leaf node. After getting into the leaf node only, it will do the backup. Until it reaches the leaf node, it won't do the backup. So this cutting off search, what it says in the sense, don't go up to leaf node, you cut off somewhere in between. That cutoff point you have to decide. So the leaf node may be at the depth 100. So that doesn't mean that we have to go up to that level, and then we have to make the decision. So in if you do that, then the algorithm will become more complicated. Not only that, in real time also that is not possible. You don't have that much time. So depending on the time constraint, we have to cut off the search at some point and then make a decision, right? So don't go up to terminal. So here terminal is replaced by some cutoff. Instead of utility, use the evaluation function. At at the terminal node, we have utility value. So don't go for terminal node means we cannot use the utility value. Instead, in between at the cutoff node itself, apply some evaluation function. Okay. So these evaluation functions are similar to the heuristic function, which we already discussed. So we have discussed heuristic functions. If you recall, f of n is equal to g of n plus h of n. Similarly, here you use some heuristic function to estimate the value of this particular state. It's an estimation. It's not the real thing, but let us estimate. So this estimate should guide us whether we are going in a proper direction or not. Or this estimate should tell like this path is how much promising this path. Okay. So based on this estimate, the algorithm will take a most promising path and it will ignore the paths which are less promising. So that is the whole thing which we are going to do. Okay. So why we are going for this cutoff search? So let us not forget the connectivity, because with alpha beta pruning we are able to achieve a time complexity of order of b to the power m by 2, but this time complexity is still not sufficient. We want to reduce further to make it practical. So we are going for cutting off search. So what is meant by cutting off search? Don't let the search go up to the leaf node, rather cut off somewhere in between. What is this cutoff point? This cutoff point we have to decide. So this cutting off search is nothing but it is similar to depth limited search. If you recall, we have learned depth limited search. In depth limited search, what we say, you limit the depth to a particular level L. Your maximum depth may be 100, but you limit the depth to 10. It means the algorithm will check only up to the depth of 10. So this is also similar to that. The now our alpha beta pruning will go only up to depth 10. From at depth 10, but at depth 10 we don't have any utility value. So what it should do, instead of utility, it should use evaluation function, and it should evaluate and it should estimate the value of this particular state, and that should be backed up. So that is the whole concept of cutting off search. Okay. So does cutting off search will add any value? So let us assume that we have set up a cutoff value of m equal to 4. Okay. So cutoff search say what it says, you cut off the search at a particular level. Don't go up to leaf node. So let us assume that we have set a cutoff value of m is equal to 4. If m is 4, then what is the time complexity? Is order of b to the power m. See, this itself is a big number, but still order of b to the power m is b is 35 in case of chess. So it is 35 to the power 4. It is this much, 15 lakh 625. So if there are, if you go up to level 4, then you will have this many states. Okay. But uh, so 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 it is a so so but this is but this is solvable by a computer. With m is equal to 4, it is typically solvable by a computer. So this is some observation. A normal human in a chess game can think up to this level, up to 4 ply. So ply means half move. A typical human can think up to his maximum his next 4 moves. Okay. If I make this move, then opponent makes this move. That is one move, and it is one ply for me. I have made only one ply. Okay, like that 4 times. Then what's the second time my move? For that, what opponents make, and what's the third time my move? What's the fourth time I can do? Some planning. So this like that at a depth of to a depth of 4, the a normal human can do. And a typical computer or a human master can look ahead up to 8 ply level. Okay, a typical PC or a program or a AA program or a human master can look ahead up to 8 ply level. Whereas chess games like Deep Blue, Kasparov can look ahead up to 12 play level. So they can. So the chess games which are created with 12 play level, they can beat the world champions also. Okay. So if you limit the depth to 4, if you limit the depth to 4, then it is solvable by a computer. It's practical, right? So that's the whole concept here. So this is the diagram which represents the cutoff search. So actually this is the leaf node, but here we are not allowing the algorithm to go up to the leaf node. Rather we are saying that you cut off here. So that's it. So now at this point we have to back up. So here apply the evaluation function and estimate the value for this particular state, how much it is promising, and that should be backed up here, so on and so forth. Okay. So other than that, it is very similar to alpha beta pruning, but here we apply the evaluation function and we make the estimation instead of the utility value. Okay. So how to apply this evaluation function, you may ask. So let us discuss an example with a tic-tac-toe. It's not with chess, because applying the evaluation functions in chess will be pretty complicated. So let us try to understand this application of this evaluation function with a tic-tac-toe game. Let us assume that currently we are in the position P. Now, uh, now if it is the computer's move, so computer is the max player. If it is the computer's move, then the computer will select the largest positive number. Okay. And if it is the uh, if it is the human's move, then the human will select the largest smallest negative number. So how do we so for a given state, how do we associate an evaluation function? So here we can associate evaluation function something like this: RCDC. It is the number of rows, columns, and diagonals in which computer could still win. So the evaluation function for computer can be calculated like this: RCDC. That is number of rows, columns, and diagonals in which computer can win. RCD represents rows, column, and diagonal. This last C represents computer. Similarly, RCDO represents rows, column, and diagonal in which the opponent can win. RCDO. So with this, we can calculate the evaluation function. Okay. So let us discuss an example that will be clear. So let us assume that X represents computer's move and O represents opponent's move. Assume this is one particular board position. So this is a board position, but one particular board position. Now, at this board position, what is the, if we apply the evaluation function, what is the value for X? Okay, that is for computer, and what is the value for opponent? What, so evaluation function should tell something like how the chance of winning for computer and the chance of winning for opponent. So here how we calculate the evaluation function for X, in the sense for that we are using what? C, the number of what, RCD, right? Yeah, RCDC, RCDC, number of rows, columns, and diagonals in which the computer can win. So if you see here, this is computer. So at which rows computer can still make a win? This is one possibility, and this is one possibility. Is there any other row? This computer cannot win. So I mean, this row computer cannot win. So this is not possible for computer. Okay. So I'm deleting this. So there are only two in terms of rows. There are only two possibilities for the computer. So here I'm writing 2. Similarly, with respect to column, what are the possibilities for computer? There is a possibility here. This is one possibility. This is another possibility. This is not possible. This is already occupied. So again, this is also 2. Okay. In terms of diagonal, what is the possibility for the computer to win? So in terms of diagonal, this is one possibility and this is another possibility. So both the diagonal, still it has a chance. So this is, so now add up all these things. So when you add up all these things, what you get? 6. So this 6 is the value for this board position. The evaluation function, or you can also call it as a heuristic function. The heuristic value for this board position for player X, that is for computer, is 6. So computer has the possibility of winning. Uh, this is the possibility score for the computer to make a win, right? Similarly, we have to calculate for opponent. For this board position, what is the opponent chance of winning? So at which rows opponent can score? So opponent can score in this row and this row. The middle row is not possible. So it is 2. Okay. In which column the opponent can score? In which column the opponent can score? Opponent can score uh, in this column and this column. The middle column, again, it's not possible. So it is 2. Okay. In which diagonal the opponent can score? The opponent cannot score in any diagonal. There is no chance for opponent to win in any diagonal given this board position. So it is 0. So the opponent's evaluation score is 4. Okay. So this is how. So this is one example. There is no hard and fast rules like how you go with evaluation function, but you should actually make a good evaluation function. The the better the evaluation function, the algorithm will be more efficient. Okay. So similarly, you can calculate the evaluation function for evaluation score for this board position also. I leave it as a homework. You can try it. So this is one example, like how do we go with the evaluation function. So why we are going with evaluation function? Because now we want to do cutoff search. That is, we are not going to allow the alpha beta pruning to go up to the leaf node. We want to cut off somewhere in between. So we are doing this evaluation or heuristic techniques. Right. So in a typical game, what we do, we and another important thing, it's need not it is not that uh, a particular game should have only one evaluation function. It can have many evaluation function. For example, it may have evaluation function 1, it may have evaluation function 2, like that. It may have n number of evaluation function also. That depends on the game. For example, if you take the game of chess, it will have many evaluation functions, and for each of the evaluation function you may have to give different weightages. It's not that this evaluation function uh, will be of. So the weightage represents importance. How much importance this evaluation function holds? How much importance this evaluation function holds? How much this evaluation function holds? So that is called as weightage. So you have to associate an weightage. Weightage for the first evaluation function, weightage for the second evaluation function, so on and so forth. Weightage for the nth evaluation function. So in general, these evaluation functions can be represented like this. That is, the evaluation function of S, that S represents a particular state, is W1 into F1 of S. This is one evaluation function, plus W2 into F2 of S, so on and so forth, plus Wn into Fn of S. Okay. Now, these functions we know. These functions, we only decide this function. But how do we know these weights? So these weights, actually this weight should be learned by the program. This weight should be learned by the program. Okay. Say for example, so how the program should learn. So let us assume it is computer's turn. Let us assume it is computer's turn. In case of computer's turn means it's max turn. Max means the computer want to maximize its result. So let us take only the one evaluation function f1 of s. So assume that f1 of s represents number of white queens minus number of black queen. So here computer is assumed to be white queen. Okay, computer is assumed to be white queen. Computer is assumed to be white in chess. So this is example for chess. Computer is assumed to be the white colored coins. So number of white queens minus the number of black queens. So assume currently there are two white queens. Okay, and there is only one black queen. So what is 2 minus 1? It is 1. So it is a positive number you got. So when you get a positive number, it means when you get a positive number, it means for this particular evaluation score, the computer is at the upper end. The computer is at the upper end. Okay, so still you should try to uh, what you should do. You should still try to increase the weight associated with this. Okay, and the weight associated with the negative one should be decreased. So that is what our objective. Okay, say for example, computer is 1 and this is 2, then it will be what? Then it will be -1. Okay, so in that case we want to, what do you call, in that case we want to, in that case it says that our evaluation function will go down here. So this is one particular evaluation function. Okay, fine. So here is an example for checkers game. So the evaluation function is given like this. As usual, f of n is equal to a1 x1 of n, a2 x2 of n, so on and so forth, am xm of n. So instead of w1 w2, here we are using a1 a2 am. That's it. Okay, so this is the, so this is a generic evaluation function. Let us assume the specific evaluation function used with the checkers game is f is equal to 6k plus 4m plus u. So let us not get into what is this k, m, and u. These are some coins in the chess. King, k represents king advantage, m represents man advantage, u represents undenied mobility advantage. So the evaluation function is given like this: 6k plus 4m plus u. Now, now let us assume that here there are computer acts as two players. Okay, computer is acting as two players. Both player 1, player A, and player B, both were played by the computer. Okay, player A is also computer, player B is also computer, but B is not. B uses a static evaluation function. That is, initially, so what does it mean by static? This, these are weights. Now the weight associated with k is 6, weight associated with m is 4, and weight associated with u is 1. Okay, but we don't know how much these weights are appropriate. That is, initially we should apply some weights. So that is how all machine learning algorithm works. So the entire concept of machine learning algorithm is uh, the, the entire concept of machine learning algorithm is to identify these weights. Okay, initially we don't know the weights. Initially we assume we apply some random weights. Initially we apply some random weights. So we may give, for here we may give some weights 0. 0.1, 0.2, like that we give some weights. Okay, and then we check. Say here they are assuming w1 equal to 9, or say 9. So 9, some weights we assume, and with those weight we calculate. Okay, so you, if say two queens are here and here only one queen, means now the weight is what? 9. So it is 2 minus 1 into 9. So the result is 9. Okay, which is a positive number. So which means that this is going to improve our f1 is going to improve our evaluation score. Okay, but if it is the reverse way, if this is 1 and this is 2, then this will become 9 into -1, this will become -9. So this is going to decrease our evaluation score. Yeah, it should decrease, right? The evaluation score is to calculate how good we are in that state. So in that particular state, if I have only one queen and the opponent is having two queen, then it means that opponent is more stronger than me. And when I'm writing a program, I should know whether I'm strong in that position or opponent is strong. So for this thing, it is returning -9. Are you getting? But how do we know these weights? These weights, actually these weights play a crucial role in making this evaluation function effective. So this weight should be learned. This weight should be learned over a period of time. So how the weight should be learned? That's what we are here. We are going to discuss. So in checkers game, we are starting. We are we are letting the computer to play for both the players, for player A and player B. And initially, this is the weight. The evaluation function used by A is also this, and B is also this. Okay, but we are making B as static. Static means B will not learn. B will not improve its performance over a period of time, but A will learn and improve. Okay, A will learn and improve. So whenever it assumes something is better, it will adjust its weight. So at every move, A will try to adjust this weight. If if it finds some move is better than this move, then appropriately it changes the weight. Okay. Are you getting? So it changes the weight. So over a period of time, these weights will be updated for A. Okay. The weights will be updated for A. Right. So that's the whole concept. So normally the so how long it will update? See, it will, for example, now now the learning capacity of A is limited by B's performance because B is static. B is static. B's weight is not going to change. So B is almost going to play like a same way. It is not going to improvise. Okay. So after a period of time, A will outperform B. Initially A and B are starting with the same weight, so they will be playing in par. But A learns and B does not learn. So over a period of time, what happens? A will outperform B. Once A outperforms B, see, this is interesting. Once A outperforms B, then we will make B as A. Then we will make B as, then we will make A as B. Okay, then A will become B. That is, A will become static. It is A will become static, and whatever the current weight A is having some updated weights, right? That will be given to B, and we will create a new instance of this algorithm. Okay, whatever the algorithm we are using, we'll create a new instance, and this new instance of A will use the same weight from B, current B. There is nothing but the updated A weights. Okay, so now also A will learn and B will be static, right? So now A will further improve like that. It can keep updating the weight until it reaches the optimal weight. So this is what the what you'll be learning in machine learning. So let us not get into the more details of that. So you will be taking the course machine learning probably next semester. There you will be learning all these things. Okay, but here we are giving a glimpse of that, right? So for every node, basically we calculate this. So how do we adjust the weight? So basically adjusting the weight is done like this. W is equal to W plus some delta. This is the formula for adjusting the weight. This delta may vary. The value of delta may vary depending on the algorithm. Okay. So if you want, sometimes we may want to increase. So this is called as W new, and this is called as W old. So new W is nothing but old W plus the plus some delta. Okay. So it's not always increase. It is not that always the weight will increase. Sometimes the weight may decrease also. So so this delta can be either a positive value or it can be a negative value. If delta is positive, then W new will be equal to W old plus delta. If delta is negative, then W new will be equal to W old plus minus delta, which is nothing but W old minus delta, right? So it's not that it should always increment. It may also decrement. That depends on what it learns, Okay. So and also it depends on the player. The max player always want to increase the output, and the min player always want to decrease the output. Okay. So here is an example here given. So let us assume that the del of a particular node is calculated like this. Backed up value of that particular node. Okay. Backed up values. What is the new value backed up? Minus the initial value of the node. Right. Now, if this value is greater than 0, if this value is greater than 0, okay, then what does it mean? So we are from A's perspective, we are seeing all these things. How does A changes its weight? Okay, we are thinking from A's perspective. A is what player? A is a max player. Okay, A is a max player. He learns and he improves his weight. So if del is and so so basically yeah. So A is so let us assume A is a max player. He want to increase his weight. He want to increase his score. So if del is greater than 0, Okay, then this term, what it should do, then the terms contributed positively are given more weights. There are some terms which contributed positively, their weights will be added, and the terms that contributed negatively will get less weight. Okay, so whichever the term which contributed negatively, their weight will be reduced, and whichever the term contributed positively, their weights will increase. That is what it does if del is greater than 0. Okay, so because we want to maximize our result, so when it will be maximized, the terms which contributed positively increase their weight, the terms which contributed negatively decrease their weight. Okay. On the other hand, if del is less than 0, if del is less than 0, it means it's a negative number. Okay, then what should we do? Then the terms that contributed negatively are given more weights, and the term that contributed positively will get less weight. Okay, so because we don't want to go to that path, right? Because we don't want to go in that direction, because that will minimize our score. So if del is less than 0, then the terms that contributed positively are given more weight, and the terms that contributed negatively are given more weights, and the terms that contributed positively will get less weight. Okay, so so why we are doing this, you may ask? Because uh, so this path we don't want to take. So we are, see here, actually what happens, the terms that contribute negatively are given more weights. So say that some term is contributing negatively, so for that we are increasing the weight. When you increase the weight, what will happen? They will become more negative. They will become more negative, and the terms that contributed positively, their weights are decreased. Okay, so this will become more, the value will become very much lesser than 0. So it means that the algorithm will not take this path, the algorithm will take the other path, right? Okay. So this is how the concept of learning works, right? Fine. Uh, so there are some other things I would like to say. So whatever we have discussed, this cutoff search can also be considered as imperfect real-time decisions. So what is meant by imperfect real-time decisions? In real time, you cannot, whether it is checkers or whether it is chess, we cannot allow the search to go up to the leaf node and then to backing up. It's not possible, because the depth of the tree can be very lengthy. So we cannot go up to that level. So somewhere in the middle, we have to cut off. So that can be otherwise called as imperfect real-time decisions. That is somewhere in the middle, which is an imperfect place. There itself, we have to make some decision. Okay, so that is what we are going to. So this is the same thing, but we are discussing for reinforcement. So alpha beta algorithm, it prunes large part of the tree, but still it searches all the way till the terminal state. So so searching up to that level is practically unreasonable. So basically, there is a scientist called Claude Shannon. He is a very famous scientist. He is the one who proposed something called as information theory. Right? Please go and check about this scientist. So what he says, in the sense, in information theory, he talks about how to communicate data, how to communicate data with less number of bits, communicating data with least number of bits. Okay, communication with less number of bits. Okay, so so basically he specified an upper bound on the number of bits or the number of bytes required to communicate so much of information, right? So with respect to computer chess playing game also, he has written a paper in 1950. So according to this paper, he suggested to go with the cutoff search, because we cannot continue till the leaf node. So so at cutoff point, so this is the minimax tree. This is the minimax search. Basically, alpha beta is a variation of a minimax search, right? So here we are here. This is a generalized minimax is given as a cutoff. So cutoff you can apply for minimax also. It's not only for alpha beta. So what this equation says in the sense, if cutoff point is reached, if the current state is the cutoff state, say D is the cutoff state. So if the current state is equal to cutoff state, then apply the evaluation function in that state, okay, and then back of the value. If current state is not the cutoff state, okay, and if you are a max node, then perform the max operation. If you are a min node, then perform the min operation. It is as usual. Okay, fine. So these are already we have discussed. An evaluation function returns an estimated expected utility. So it is an expected score. So inaccurate evaluation function will will guide an agent towards a position that turn out to be lost. That is, this evaluation function should be good enough. If the evaluation function is not good, then the algorithm will take you to a path which will make you as a loser. So it is very important that we should design a good evaluation function. So the question is, how will we design the good evaluation function? A good evaluation function should have all these features, these three features. What are they? The evaluation function should order the terminal states in the same way as the true utility function. What does it mean? Here, ordering in the sense we are not talking about the ordering of the tree, but uh, but it should give more priority for winning than for draw and lose. That is, the states that are wins must evaluate better than draws, okay, which in turn better than losses. Okay, so the evaluation function should be designed in such a way that it should provide better utility value for wins than for draws. Okay, and it should give better utility value for draws when compared with losses. So this differentiation should be visible explicitly so that the algorithm will take the right path. If this difference is not specified properly, then the algorithm may not be able to differentiate between a winning move and a losing move. Okay, so this is the first criteria. The second criteria is the evaluation function should not take too long time, because always we have a time constraint. And then the third criteria is, in a non-terminal state also we should be able to apply the evaluation function. And when you apply the evaluation function on a non-terminal state, the evaluation function should be strongly correlated with the chance of winning. When you apply the evaluation function on a non-terminal terminating state, the evaluation function should correlate towards winning. It should not correlate towards what you call towards draw. Because see, when you play a game, your objective is to win. It's not to draw. Only when winning is not possible, you will look off draw. Similarly, when you apply the evaluation function on a non-terminating state, on a non-terminal state, the function should be correlated towards the chances of winning. Okay. So how do we create this evaluation function? So that is the question. So to create the evaluation function, say for example in chess game, there are different features for each of the coins. Say you can calculate like how many white points are there, how many black pawns are there, how many white queens are there, how many black queens are there. This is one method of evaluation. But and so it's not only one category. So it's not only, we cannot make the evaluation function only based on pawns or only based on queens. We have to use so many things. So that's what we have discussed in the previous slide. So for example, this may be f1, number of white pawns versus number of black pawns, number of white queens versus number of black queens, that may be f2. Like that, multiple evaluation functions we should use. Okay. See, one example is given here. Assume that let us assume that uh, let us assume that the computer is having 2 pawns and the opponent is having 1 pawn towards the end of the game. Towards the end of the game. So we don't know about the other coins. So pawns, only about pawns we are talking. Pawns, there are, the computer is having 2 pawns and the opponent is having 1 pawn. Computer is having how many queens? We don't know. Computer is having how many bishops? We don't know. How computer is having how many rook? We don't know. Opponent is having how many queens, bishop and rook? All these things we don't know. But based on this pawn, there is a evaluation function. Say based on the experience, it is said that 72% of the time, if you have two pawns and the opponent is having one pawn, you will win. So 72% of the time you will win. That is a utility of +1. 20% of the time you lose. That is a utility of 0. 18% of the time the game will draw. That is a utility of 0.5. So for this particular case, so it is only one feature. So let us assume it is f1 for based on only pawn. Then the evaluation function can be written like this: 0.72 into 1 plus 0.20 into 0 plus 0.08 into 1 by 2, which is 0.76. Are you getting? Like this, actually, we should create evaluation function for every other coin also. So this is the expected evaluated score. So this is the estimate, right? So evaluation score is an estimate. The expected value can be like this. We have to determine for every category. This is only for the category of on. But if you want to do like this, it needs you should have too much experience. So you need a chess expert, and with a lot of experience, only this can be done. So this is same as what we have discussed previously. So mathematically, this can be represented like this. The evaluation function is nothing but W1 F1 plus W2 F2 so on up to Wn Fn, and this can be summarized like this: sigma I equal to 1 to n Wi Fi s. Right. So here we are using actually various functions. So it's not one. So this whole evaluation function actually it includes multiple category of evaluation, multiple category of functions. Okay. So one method is we can. So how will we associate with W1? What is W1? What is W2? How will we know this W1, W2, W3? All these things. So one method is, so if you read the basic books on chess, then it gives some points, right? For pawn, the point is 1. For bishop, the point is 3. Okay. So if this f1 is about pawn, then this w1 you can assign 1. If this f2 is about bishop, then you can assign 3. Okay. Similarly, if f2 is about queen, then queen value probably you can assign 5 or 10, whatever it may be. So that is one way of assigning the weights. But then it becomes a static weight. Then it becomes a static weight. For example, you cannot always give 3 to the bishop, because initially 3 to a bishop may be fine, but towards the end of the game bishops become more powerful. Okay, when there are more places it can spread out. So here actually we should use machine learning to learn these weights. So as we have discussed previously, we cannot fix any static weights. Initially we can fix some static weights, but over a period of time we should use some machine learning techniques to learn these weights. Okay. So cutting off search is nothing but a modified version of alpha beta search. Here we use a heuristic evaluation function when we want to cut off. So we can use, so for performing cutoff search we use depth limited search, but instead we can also use IDS, iterative deepening search. With IDS the ordering also we can achieve. Okay. With IDS, two things we can do. Only one thing is we can do imperfect evaluation. So imperfect evaluation is nothing but cutoff. Apart from that, we can also go with perfect ordering, and hence IDS will be more robust. Okay. So that's it about this particular lecture, this particular topic, that is adversarial search technique. So we'll stop here. Thank you.